layers. This is joint work between University of Cambridge and Toshiba in the UK. So to kind of motivate the problem, suppose somebody one day sends you a data set which is full of images. They may be, for example, artifacts from a museum, or images of concrete surfaces from a tunnel or from a dam or a motorway or something. And then later on in time, a few months or years later, they send you another set of images of the same scenes, which may be roughly registered but not precisely, taken under different illumination conditions, taken with different cameras. And the task is to identify and quantify the changes in these data sets in an automated way, because these are large data sets. So why is this difficult? It's difficult for humans because our vision is governed by an attention mechanism, and I can see that already some people aren't even looking here, so they wouldn't detect changes here. And similarly, if inspectors are looking at large data sets of concrete panels, they're going to eventually lose their attention, or they'll be distracted by certain things, and the performance of humans can be quite poor for these kind of problems. And there's also a lot of subjectivity, and so if you show the same data set to a bunch of different people, they may all come up with different results. So we want an automated method, but this is also a hard problem for machines. It's hard because there's not just the variation that you're trying to detect, but there's a lot of nuisance variation. So the cameras are in different viewpoints, there are changes in the lighting, there are changes in the sensor being used to capture the image, there are changes in the focal settings. All of these add up to a huge amount of image variation. So in order to detect real changes in the scene, we need to be invariant to that. And one way to do it would be to design a feature which has these kind of invariant properties. So using deep learning, for example. But we wanted to have a more principled approach, which is a bit more transparent in terms of what's happening in our system, so that we can debug it and understand it more easily. So our approach assumes smooth surfaces. That's the main assumption of it. This is not necessarily a strong assumption. We can loosen it, but it applies in most of our scenarios. For example, looking at concrete panels. And then we try to compensate explicitly for the three main sources of nuisance variation. So specifically viewpoint, we use sub-pixel registration using a version of generalized patch match. And we use the correspondence from that. We fit a thin plate spline over the top to regularize the flow, and that gives us our registration from time 1 to time 2. Then we fit a second thin plate spline over the lighting bias to take out the variation from lighting. And finally we optimize over a blurring kernel to kind of get rid of image gradient differences caused by focal differences in the two times. So the pipeline, I think, is quite simple to implement and understand, and it gives quite nice results. So I'll just show you a graphical representation of what's happening. So given a couple of artifact images, so this is a statue in, I think, in the Summer Palace in Beijing in China. And our approach is first registering the two very precisely using patch match with a circular NCC cost. And then from the correspondence we estimate the surface of the object, we fit a sampling grid to it. And using that sampling grid we fit thin plate splines to take account for the flow, to smooth it out over areas which have sparse features, and also for the lighting. And then we apply the gradient compensation step, and I'm happy to take you through any of this at the poster. And then finally the warped original image is compared to the previous image, and you get a change map out, which hopefully is very similar to what you're after. So to justify the pipeline, another couple of example images where each stage, firstly the geometric correction, the photometric correction, and then the focal correction are added in. And you can see that the change is becoming more obvious with each step of the pipeline, and finally resulting in a process which gives quite nice and pixel precise changes. And so this is suitable for things like skin condition monitoring or detecting fine cracks. And finally, a comparison against the state of the art, which is a publication from ICCV last year. Our method performs quite similarly, better on certain data sets, worse on others, but it's a lot faster, a lot more efficient, and a lot easier to understand what's happening. So yeah, so I've presented this patch match thin-plate spline approach to precise change detection. There are many possible applications for it, which I think are quite interesting, and I'm happy to answer any more questions at the poster. Thank you.